Hi, this is your instructor, Mr. Jerry Pinter. Welcome to our first lecture of EE 303. Chapter 1 is an introduction to signals and systems. In part 1 of this lecture, we'll look at some basic definitions and concepts of signals and systems. Chapter 1 is broken up into 4 parts. In this video lecture, I'll cover part 1. 3 separate videos will cover parts 2, 3, and 4. Please watch these 4 videos in their correct order to get the most out of them. Let's start by looking at the hierarchy or levels of electronic theory. The lowest and most fundamental level is called the device physics level, where the various electronic components are explained in terms of their physical properties and electrical characteristics. For example, here's a diagram of a bipolar junction transistor with its doped semiconductor layers that make up the emitter, base, and collector terminals. It also shows the transport of charge carriers, such as electrons and holes going through the device. As you'll learn in a class that covers device physics, a transistor like this can be characterized by its current gain, which is a parameter called beta. And beta is the ratio of collector current, IC, to base current, IB, and it's given by this formula here that contains things like the diffusivities of the electrons and holes, the doping levels in the emitter region here and base region here, and also the physical dimensions, the width of the emitter and the base. So this is the lowest level or most fundamental level to understand electronic theory, and this is something that is covered in, for example, a course like EE 330, which is electronic circuits, or maybe you've taken another course, solid state physics class, that has semiconductor device physics. The next level up is the circuit level, and this would be covered in classes such as EE 280, Introduction to Electronics, or EE 330 again, Electronic Circuits. At the circuit level, we represent this transistor here with just its circuit symbol here, which is shown right here, and the transistor might be connected to a variety of resistors, capacitors, and power supplies. And this is a schematic diagram of a basic amplifier circuit where the gain of the amplifier is defined as the output voltage taken here divided by the amplitude of the input voltage taken here. And there's a formula that can be derived to calculate that gain, which is based on the various external and internal resistances of the circuit. So these 2 levels here are certainly important, but this is not what we're going to be covering in this course on signals and systems. We can go up another level, and this is particularly important for digital electronics, such as in EE 301, and this is the so-called gate level of electronic theory. And here, we represent the various logic gates, such as AND gates, NOR gates, inverters, and so forth, with these logic symbols here, which are interconnected to show the flow of bits, binary zeros and ones, going through the circuit here. So the highest level, and the one that we're interested in this course, is the so-called system level. And this is what we're going to be doing here in EE 303. This is an example of a system level block diagram of a radio receiver here. So each of these components here that are shown represented with these boxes have lots of circuitry perhaps inside, which we're not really concerned with. We just want to know how each of these handles the signals going in and coming out of each of these subsystems. So for our radio receiver here, we have some input signal, which is in the form of RF, radio waves, radio frequency waves, that are picked up by an antenna. The antenna then sends those signals to a tuner here to select the station that we're interested in. The selected station then might go into a detector to demodulate the modulated signal that's coming in from the antenna, and then that demodulated signal from the detector might go to an amplifier to increase the power of the signal. And then finally, that signal might be filtered. For example, this could be something to remove noise or to boost the bass or treble or something like that. And the final output signal here is the audio signal that will be converted to sound by a speaker or headphones. Let's start by looking at an introduction to signals and systems. So our first thing is to ask the question, well, what is a signal and a system? So signals contain information. A simple example is if you think of an old telephone, like a landline, the voice information, when you're talking to somebody on that telephone, is basically coming through the wires as a time-varying voltage. And, the old-fashioned telephones basically took that voltage and turned it back into sound. Today, things are a little more complicated, obviously, with digital cell phones and so forth. But this is the idea of a signal which just contains the information that we want to send. So signals can be modeled as a time-varying mathematical function. So typically, we will be dealing with x of t, where x represents an input of a system, and y of t represents the output signal of the system. And notice they are both functions of time since they are time-varying. Now, what about a system? Well, a system basically responds to the signals. One way you can think of this is a system processes signals. And a system usually, almost always, produces another signal. So for example, the radio receiver tuner amplifier we talked about on the other page took a signal coming in, basically electromagnetic waves coming from the transmitter, and it did some processing to those signals and basically produced a sound wave coming out, which is voice or music, something like that. So a system is modeled as a mathematical equation, and the input and output of this equation are the signals. So here's our block diagram of a basic system, and we're going to be seeing this diagram over and over throughout the course. So it's make sure you understand this, but it's pretty basic. Over on the left, we have our input signal, which is typically denoted x of t. And that, you can kind of see the arrows represent the flow of that signal into our system. So the system is whatever is in this yellow box here. And then the system processes that information, the input signal, and spits out an output signal, which we designate as y of t. So this is sort of our basic notation that we're going to be using in this course to represent a system. So signals can be basically classified into two types. There are continuous time and discrete time signals, and we are going to be pretty much giving equal share to these two types of signals in this course. So let's start with a continuous time signal, because this is something you're probably most familiar with. Remember, we can represent a signal as a mathematical function. So in this case, our signal is called x of t, and this is basically the function x of t. You can see it's a continuous smooth line here, and this continuous time signal, which is a mathematical function, it has a single value for all values of time. So if we want to know what is the value of this signal at time 0, obviously we can just read that off the graph. So this point right here could be represented as x of 0. Likewise, if we want to know what the signal is at 3 seconds, we can read that off the graph right here. And this value, whatever that value is designated x of 3. On the other hand, there are discrete time signals. And by the way, discrete time will be abbreviated dt, whereas ct is for continuous time. A discrete time signal is often called a sequence. So you'll hear me, and you'll also see the book, use these two things, these two terms, sort of interchangeably. They basically mean the same thing. The reason it's called a sequence is you can see that a discrete time signal or sequence is a sequence of values, and there's one value for each index n, where n is a dimensionless integer. So n, you can see this is down here. We're plotting this signal not versus time per se, although these are in sequential, so they are in order. But our independent variable here, or our horizontal axis,
is the index n, which you can think of sort of as a placeholder or just a counter. That's why I also will call it an index here. So for example, in this sequence here, you can see the sequence is represented by these dots here. They represent the value of the sequence at each value of n. So right here in the middle here, whatever this value is here, that's x of 0. The next one would be x of 1, x of 2, x of 3, and so on and so forth. You can see we can go to the left side, just like going negative time. We can also go negative values of n. So this is x of negative 1, x of negative 2, and so forth. I should also point out that in between these values, there is no defined value. So in other words, there is no signal between n equals 0 and n equal 1. It's not equal to 0, it's just undefined. So the actual values are the black dots shown here. So this is a case or an example of a discrete time sequence. Now, one thing also is that a discrete time sequence like this does not necessarily mean it's a digital signal. In fact, the values of x of n here can be any value, and that would make it technically an analog signal. Now, it could be digital, in which case the values of these sequence numbers here would actually be represented by bits, for example, an 8-bit system or a 16-bit system, depending on how much resolution there is. But we're not going to, confuse the fact that it's discrete time with it being digital, because it is not necessarily a digital sequence. One way to sort of see the relationship between a continuous time and a discrete time sequence is through the use of sampling. And this is something we're going to look at in much more detail later in the course in Chapter 7. But from now, we can think of that a discrete time sequence, x of n, is often constructed from samples of a continuous time signal, x of t. And by the way, I didn't mention this on the last slide, but I should do so now. A sequence, which is x of n, this is a discrete time sequence, the index n is put inside of square brackets always. Whereas a continuous time signal, like x of t, notice the t, the argument of the function, is put inside of parentheses like this, the curved brackets or parentheses. So that's kind of one way to tell, just by looking at it, whether it is a sequence or a continuous time signal. But anyway, what we have here is we're showing that we start with x of t, which is the smooth blue line. And if we take samples of x of t at an equal interval, and then, by the way, that interval is called the sample period, uppercase T, all right, then we can construct a sequence, a discrete time sequence. So these black points here represent samples of our original continuous time signal, x of t, and it produces a sequence of values which we can call x of n. And notice, the spacing in time between two samples is called the sample period. So we'll refer to this, we'll use this from time to time to sort of make a connection between a continuous time signal and a discrete time sequence. The next thing we're going to do is talk about some of the properties of signals. For example, one of them is called time shifting. So if we start with a signal x of t, which is shown right here, if we basically delay this signal by 2 seconds, then it's going to be shifted over on the time axis like this. So it's the same shape as over here, obviously. We're just shifting it to the right by 2 seconds. So mathematically, this is x of t minus 2. Okay, so this is x of t. When we go x of t minus 2, that has the effect of delaying the signal. By the way, if we add 2 instead of subtract 2, as you can probably guess, this thing is going to shift to the left, and that would be an advanced signal. This is an example of a discrete time sequence, x of n, and down here it's been delayed by meaning we're pushing it or shifting it to the right by some value n naught, okay, and that can be any integer value here. So this is up here, if this is x of n, this sequence here, then down here this sequence would be x of n minus n naught. One of the other properties that we can do with time is a time reversal. So in discrete time, for example, let's say we have this given sequence of values here called x of n. What does x of negative n look like? Well, notice what we're doing here is we're taking every value of n and we're reversing its sign, okay, to get x of minus n. So this is called a time reversal. And notice what it does is it simply flips the sequence about the y-axis, okay? So all these points here, like what x of 4 up here now becomes x of negative 4 down here. So there's sort of a flipping, almost like a mirror image effect here. So for continuous time, same idea. If we have this signal here, x of t, let's say it looks like this, then the signal x of minus t is a time reversal. So that means we just flip this signal about the y-axis to get this result here. So we can combine these effects of time shifting and time reversal. Let's take a look at an example here where I've shown the signal x of t is sort of like this step function right here, and this will make it a little bit easier to see what's going on here. So this is our original signal x of t. Now we've already seen that if we go x of t minus 2, we're simply delaying the signal, which means we push it to the right, we shift it to the right by 2 seconds. So this edge here, instead of being at 1, the edge is now at 3, and we get this result. Likewise, if we do x of t plus 2, we're basically advancing the function x of t by 2 seconds, meaning we're going to push it to the left to earlier times by 2 seconds. So now you can see the edge is at negative 1. So over on this side, we've got the time reversal. So remember, this is x of t here, then x of minus t is simply time reverse, so that means we flip this function about the y-axis to get this function here. And notice now, the step is not only over here, but the function goes to the right, whereas over here it went to the left. So when we do x of 2 minus t, what happens when we're talking about this is, remember, this is time reversal, because notice the minus t. When we add 2 to that, this shifts this to the right by 2. So we get this function right here. And one way to kind of check this is always to see where the edge occurs. So remember here, when the argument of the function is 0, the edge is at 1. So notice if we take t equal 1 here, we have 2 minus 1, then that's the same as this edge here. But notice this one combines both time reversal and also shifting to the left. So this is x of negative t minus 2. And notice now the edge is over here at negative 3. So, the time shifting and time reversal by themselves are pretty simple properties of what we can do with a signal. But when we combine them like this, it can sometimes get a little tricky, and we just have to be careful that we're shifting things the right direction. One more thing we can do, and this happens quite often, is adding and subtracting signals. And this is reminiscent of superposition, which you learned about in physics. For example, when you had 2 waves on the same string, or 2 sound waves traveling through the air at the same time, we add those 2 waves together and use the principle of superposition. So we're basically doing the same thing here. For example, let's say we're given these 2 functions, x1 of t, which is shown right here, looks like a triangle, and x2 of t is shown over here. It's sort of a rectangular pulse shape. All right, so if we're given these, let's say we want to plot x1 of t plus x2 of t. Well, that just means we're going to take this signal here and add it everywhere at each time, we're going to just add the two values together to this rectangle. And so you can see here very clearly what happens is the triangle now is sort of sitting on top of this rectangle here because we're adding it. And so this is the result. Now what about if we take x1 of t here and subtract x2 of t? In other words, take this away from this. What do we get? Well, what happens is we end up with this right here. And this may not be quite as obvious as doing addition over here. One way to do this, sort of a trick, is to sort of start. You remember we're taking this function here and we're going to subtract this one. So start at 0 and let's just move to the right in time. So at 0, notice this function is 0, but we have to subtract 5 from it. So that's why it starts at -5. Now, this thing increases up to 5. So that means this thing is going to increase. Now notice when we get to 1 second, we have 5 here and 5 over here. So those subtract from each other and we end up with 0 right here. And we can just keep going along, by, sweeping kind of to the right and comparing the value over here to the value here and subtracting them accordingly, and you'll end up with this function right here. Quite often in this course, we're going to sort of take a pause in the lecture and have you guys do some activities just to make sure that you understand the concept. So these are sort of like little mini quizzes or knowledge checks to make sure that it's all making sense what we're doing. Normally, if we were in the classroom, I would have you guys work together in small groups to come up with the answers, and then we, would typically go over those. But we can sort of do the same thing here by virtual instruction. You can work on this at home. And we'll be doing this, throughout the course. We'll be doing some activities like this. So typically, I will show you an example of how to do something, and then I'll have you guys perform another example or an activity to test your knowledge there. So here's our first activity. We're given this continuous time signal here, x of t, that looks like this sort of step function here. And there's two tasks. The first one, you're supposed to sketch the function x of t minus x of t minus 4. And the second part of the activity, sort of a separate problem, is to sketch x of negative t plus x of 2 minus t. So go ahead and pause the lecture here and go ahead and do these activities and see if you can get the answers here, and then we'll go over those. What you'll probably need to do, unless you've completely got this down, you might want to go ahead and go back to the previous examples I showed to see how to do this. We'll resume shortly. All right, so here are the solutions to our first activities. So the first one, we were supposed to sketch x of t minus x of t minus 4. So again, here's x of t, which was given to us. X of t minus 4, remember, that's a time shift. We're delaying the signal by 4 seconds, so it's going to be over here. The step, instead of at -2, it's now at +2, and we're asked to subtract this value here from this value here. And what we do when we do that, we end up with this sort of rectangular pulse that looks like this. So this is our answer to the first one. And if you had trouble doing that, the way, remember, to subtract this function from this one is start over here. Notice the value is 1. Here the value is 0. So therefore 1 minus 0 is 1. And you can keep going across here and you'll see that the value is still 1. But once we get over here in this region, I have 1 up here and 1 down here, so when I subtract it, it goes to 0. And the same can be said out here. We have 0 minus 0 is 0. So all that's left when we subtract the two is this rectangular shaped pulse, which is shown here. So the next one is maybe a little more tricky. We're supposed to sketch x of minus t, which I sketched right here, and then add to that x of 2 minus t. So the first, the way to do this is to sketch these two signals, lay them, sort of overlay them like this, one over the other, so that we can add them. So this is x of negative t. This is just a simple time reversal of this function here. So we just flip it around the y-axis. This is x of 2 minus t, and for this one, it's not only a time reversal, but it's shifted to the right by 2. And then when we add these two together, we sort of get this stair-step feature or stair-step shaped function here. So this is our final answer to the second activity. There's one other thing we can do with time, and that is called time scaling. So if we have our original signal x of t, kind of looks like this bell-shaped curve right here. If we plot x of 2t, what we're basically doing here is scaling time by a factor of 2. And this has the effect of basically shrinking the width of our function. Notice it has the same height as up here, but the time scale has been shrunken down by a factor of 2 when we plot it like this. Likewise, if we go x of t divided by 2, this has the effect of stretching it out in time. So our original signal up here is going to be stretched out to twice its width here. Now we're going to move on to a special class of signals that are called periodic signals. So a periodic signal has a definition. Let's look at the definition in continuous time first. The definition of a periodic signal is when x of t is equal to x of t plus m times t naught, where m here is any integer, in other words 0, 1, 2, 3, 4, or it could be negative as well, and t naught is called the fundamental period. And for a continuous time signal, the fundamental period can be any number. It doesn't have to be an integer. But the key thing is that this has to be an integer. So what this is saying is that the function has the same value if we go some number of periods either ahead in time or back in time. So a periodic signal basically is pretty easy to recognize. We just see the same pattern repeating itself over and over. So this is an example of a periodic signal. We can see this sort of bell-shaped curve here repeats. And notice it repeats every period, which is designated by the uppercase T here. So this is one period. Here it's again repeating again at 2 periods, and we would keep on going to the right, and also it keeps on going to the left. This is at negative t, negative 2t, and so forth. The distance between any two points on these curves, for example, from peak to peak, is by definition the fundamental period. And notice I'm using t naught here. The book just uses uppercase T. They basically mean the same thing here. Now, for a discrete time sequence, we can also have a periodic signal or sequence, and the definition is very similar. X of n has to be equal to x of n plus m n naught. So again, m is any integer, and n naught is our fundamental period for our discrete time sequence. Now, the one difference here is that for a discrete time sequence, the fundamental period has to be an integer. Because remember, the time axis for discrete time sequences is n, and n takes on only integer values. In other words, n equals 0 here, n equal 1, n equal 2, 3, 4, 5, 6, etc. There is no such thing as n equals 1.5 or n equals 3.2. All right, that's for time, that's okay. But for discrete time sequence, obviously n has to be an integer. Therefore, the period of a periodic sequence also has to have an integer value. So here we can see an example of a discrete time periodic sequence. Notice this pattern, 2 up, 1 down, 2 up, 1 down. It's repeating over and over and over. This particular sequence has a fundamental period of 3, because you can see that it repeats itself every third value of n. So here's our next set of examples for you to work on and test your skill here, this time on periodic signals and sequences. So the first one, there's two of them here. The first one, you're given this x of t. You're asked to sketch a periodic version of this waveform here, or this shape, and the fundamental period is 5. So go ahead and just sketch about, let's say, 3 or 4 repeating versions of this with a period of 5. And then the second one is a discrete time example. You're given x of n, which is this little segment of a sequence right here, and you're asked to sketch a periodic version of this with a fundamental period of 4. So go ahead again and pause the video here and see if you can do this, and we'll look at the results next. So here are the solutions to the activity. So for the first one, the continuous time version, you were asked to make a periodic version of x of t. So here is the solution. This is the original shape here. Notice, in order to get a fundamental period of 5, we have to make sure that, for example, this edge here, which is at 2, the next edge would have to be at 7. The preceding one would have to be at -3. All right. Likewise, where it starts here at -1, we can add 5. Notice this is the fundamental period, 5 right here. So it would start at 4. And then over here would be -6. For this one down here, this is the x of n. The original one was just these two values right here. This is the periodic version of it with a fundamental period of 4. So we started at 0 here. That means the next one has to repeat at n equal 4. The next one would repeat at n equal 8, and so forth. Likewise, going on this side, we just subtract 4. So if we started at 0 here, we start at -4 here. So these are our two solutions to those activities.